Hi, my name's George. I'm here representing Hackworth. We're a small company of currently 3 developers, one of whom is over there and one can't be here, based in London. And our goal is essentially to broadly improve the state of computer science education, make it accessible and fun and cross-curricular. And we've got all sorts of ideas about tools that we would build to achieve that, given infinite time and money. But the first step is basically we need the right programming language to start off with. And while there are currently languages out there that are designed for teaching, such as Racket or Scratch, none of them quite fit our preferences. We're all Haskell programmers. We're all very sold on the benefits of statically typed functional programming, and that's not the direction in which bespoke teaching languages have tended to go. And in particular, we do think that there are benefits to static types and functional programming in an educational context. We think it's easier to reason about programs. We're all familiar with the ways in which GHC can help you. It can explain to you what is currently wrong with your program at compile time, much more so than would be the case in some languages that are popular in classrooms, such as Python, where you're kind of on your own. And we want to bring that to the educational space. But we don't think that something like Haskell is directly all that suitable as a first language, at least sort of below university level, because there's a lot of cruft. There are a lot of features that you might want to tell someone to ignore from the start. There's tooling issues, etc. So we've built a... Oh, sorry, I forgot to start my stopwatch. How far are we? We've built a language from the ground up called Primer. It's a statically typed functional language, and it's designed to be used via a structure editor. So I don't know how many people here are familiar with what structure editing means. That's less, no, it's better. Okay, so it's sort of building on the idea of an IDE which can tell you all sorts of things about your code, but actually, rather than even having a text-based language to begin with that then gets parsed by a compiler, you're directly manipulating the abstract syntax tree of the language instead. So Scratch, are people familiar with Scratch? The teaching system? Okay, so Scratch is when we talk about programming in education, Scratch is often the thing that people mention. Scratch has been very successful in getting into the hands of kids and getting into classrooms, but it does not value the kind of things that we value in a programming language. It's a sort of weakly typed imperative DSL for animating cats, basically. It's not very, it doesn't have that broad applicability. It can be used for games more generally. But one of the things it does get right is that it uses a form of structure editing. You put together blocks where you have primitive blocks that are variables and values, etc., and then larger blocks which are control structures, and the visuals of the language kind of guide you into what things can plug in where. And this is very helpful because syntax is a barrier for complete beginner programmers. I'm sure we've all been there. The first thing you have to learn before you can really get anywhere is the syntax of a language. And when you have syntax errors, the compiler doesn't really tend to give you very useful information about what exactly is wrong, because you're giving it something that doesn't make any sense to it. And so structure editing allows you to overcome that particular barrier. And we've taken the obvious approach with a functional language, which is for that structure editor to be tree-based, to literally represent the abstract syntax tree as a tree. The alternative is text-based, which we would like to also support. In a prototype, we had the ability to also view our program trees as text, but still manipulate them structurally. We haven't yet re-implemented that for this version. But that system ends up looking a lot like Hazel, which I don't know if anyone's familiar with Hazel. Okay, wow. It's sort of as far as I can tell, the most advanced sort of functional structure editor that's out there. And we've taken an awful lot of inspiration from Hazel. So this is, if you want to look into it, this is Cyrus Omar's group at Michigan. They've published a lot of papers about structure editing in a strongly typed language. And in particular, they've kind of shown us the way on how to build a system in which there are no meaningless editor states. You can never have static errors as such. If you try to insert, say, something of the wrong type, Hazel will put that in a hole, which is a lot like the kind of typed hole that you get in GHC, and you can kind of work around it, and it will tell you what you can do to fill in these incomplete parts of a program. So, without further ado, I'll begin demonstrating Primer as we've built it so far. So this is still It's a work in progress. It's the core ideas are there. There's all sorts of cleanup we can do visually, but here we go. So this is a completely blank canvas. We're going to start from scratch. We can build up. We have a standard library that we can optionally use, but for the purposes of this talk, I'm going to build everything completely from scratch, including Boolean types, etc., because we can. We do have primitives, but that's a crutch because we did some demos about a year and a half ago, and a lot of people told us, hang on, people want to work with integers and characters, and we're like, okay, we'll add them. We couldn't sell teachers on the idea of using inductive natural numbers in a first programming class, which is probably fair enough. Right, so I'm going to build some fairly simple types and functions and show you how the UI works. And unfortunately, we're not going to get to anything particularly complicated because of time constraints. So apologies if this isn't the world's most interesting program. So on the main view here, this is our canvas on which we build programs. And over here, we have our actions. We interact with, we build programs via a discrete set of actions rather than spending much time typing text. That's sort of the basis of what structure editing is about. So we'll start off by defining sort of the most simple, interesting type you could have, which is a Boolean. So this would currently be isomorphic to void. We need to give it some constructors. So add one constructor called false and another called true. And this is a Boolean type. We could have more labeling here, explain exactly what's what and labels on edges, etc. We intend to do that, but hopefully with an audience here where everyone is familiar with ADTs and functions and functional programming, it should be reasonably clear what's what. So if we then want to build a value of that type, we can add a term definition. We'll call it B, and here we have the type of the definition and the term. The type is going to be bool. Notice here that when we're in a normal language, in a non-structured editor, you would then have to type in the value that you want to use at use cases. We're able to list all of the things that are in scope instead. And this one of the many advantages of this is, as I'm doing right now, it's very useful on touch screens. You spend very little time typing. And in a lot of classrooms these days, kids are primarily on iPads rather than traditional desktop PCs. So that's handy. And we can insert a value here. And the constructors that we have in scope are true and false. So this is very simple. This is basically saying B equals false as a top-level definition. And just to show you the other parts of the UI, over here we show some info about the currently selected thing. So here, this is a Boolean. It has kind type. We might want to display that differently. And this is a Boolean. And in this tab, we can evaluate a definition. This isn't going to be very interesting because B just evaluates to false because there's nothing there to run. But we'll come to more interesting definition afterwards. Okay, then I'll quickly, and I'm going to have to race through some of this in the interest of time, but I'll quickly define a more interesting type. List. List has two constructors, nil and cons. We want to make this polymorphic list, so it also... Aha. So you'll notice down here we have this level toggle. So we currently have 3 levels. There's a sort of intermediate, expert, and beginner mode. And in the beginner mode, the list of actions that can be applied is very small. We want to not overwhelm students who, in our target audience, are complete beginners to programming with features that they don't yet need. For this demo, we're going to have to briefly go into expert mode in order to define a polymorphic type. Wait. That's expert mode. We should make that more intuitive. I think there is a hover on it. Yeah. Just rename that. Try and be conventional and give that a lowercase name. A list is either nil or it's cons. Cons has 2 fields. There's A. Again, we show here just the things that are in scope. And, yep. Is that good? Okay. Yeah, I'm trying to get a lot of information on screen, but it's no use if no one can see it. Okay, this is the definition of a generic polymorphic list. We're currently using the left-facing arrow for function application. That might be subject to change. A lot of the sort of visuals, I'll say, are subject to change. We were for a while using Haskell style @ and $, but that's sort of a bit jargony. No one really, especially $, no one really uses that outside of this community, so we can choose something that might be more intuitive. So this is a list, and let's now, for the first time, define a semi-interesting function. I'll try and do this quickly. I'll cheat and define a monomorphic list in the interests of time. So we're going to go a monomorphic map. So we're going to go from Booleans to some abstract custom type, which we'll just call T, with a single constructor T, and we'll expand this afterwards. So we want to define a map over lists from Booleans to T's, and as we know, map transforms that into a function over oh, that's not supposed to happen. We have a bug with undo. You can blame him, I think. No, I think it might have been me. Oh, I've done the wrong thing here. Okay. As I say, there are all sorts of ways in which this UI could be slightly more intuitive, but it's worth stating that this is all designed for... When we talk about teaching, we're talking about teaching in classrooms. So this would obviously, as it stands, be completely overwhelming to a beginner. They wouldn't know where to start or how to do anything sort of useful with it, but we will have a curriculum that talks them through defining basic types and functions and gradually building things up. We haven't really done that yet. It probably would be roughly based on the how to design programs curriculum, if anyone is familiar with that. Let's get someone. So this might look vaguely familiar as the type of map, or of a monomorphized form of map. Okay, let's build a function. This is map. We take a lambda. Note that.
Can you zoom the main canvas?
Yeah. If one is at lambda here, the primary is clever enough to realize that this is a function and give us some useful naming hints. So we can call it f. We take a second input, which it's not quite clever enough to work out that this shouldn't be should be conventionally called something more like x's. This is actually just because we defined list ourselves. In our standard library, we do have name hints attached to other types, and it's actually quite useful. Beginner students are very, very bad at naming variables. I mean, a lot of us are very bad at naming variables, I'm sure, but students will, if left to their own devices, name everything x. So we want to discourage that sort of behavior. And then, okay, we're going to want to do something with x's. And for the first time, Primer has told us, oh, you can't put x's here. This doesn't make sense. This wouldn't be type correct. Because this has the type list of Boolean, but the tree as a whole is expecting to be something of type list of T. And this is what we mean by there are no invalid editor states. What we do instead is introduce holes, show parts of the program which are currently incomplete, and then allow the student to work around those. So we're going to want to do something with x. We're going to pattern match on x. This is, again, slightly unintuitive UI, but this is what pattern matching looks like. And we should just add a bit more labeling and stuff. But it automatically generates the cases, so it knows that because x is a list, there's a nil case and a cons case, and this is map. So in the case of nil, we're going to insert nil. We've highlighted the things that are of the correct type, just to guide the student towards the correct solution. And here we'll have cons, and the thing that we start off with is going to be f applied to the first element of the list. I'll rename these to more intuitive names. So we want to apply f to something of type Boolean. That's going to be y. And then we have the rest of the list where we're going to want to apply map recursively. Note that the spine of the application here has been automatically generated because, again, Primer knows the type, so it can assist students towards building the correct sort of shape of program. This is a function that's going to match the type of f. Again, that's highlighted. Insert f, and then wise. This is a complete definition of map. And if we've got time, I'm going to briefly show evaluation of a simple program, and I might just rush through this without explaining too much what I'm doing. We're going to want a list of our output type, and we're going to achieve that by applying map to some input list, which we're going to have to construct in a slightly laborious fashion because this all goes from first principles. What we would like to do here, ideally, is for certain types, like lists, be able to show other kinds of projections, so showing a list in a way that looks more like a list. For the time being, the only projection we have is to show everything as a literal sort of tree built up from scratch. So this is a list containing, let's say, 1 false and 1 true. What's the function that we're going to map? We don't have time to do anything interesting, so we'll do something with x. In the case where it's true, we'll have a t, and in the case where it's false, we don't know what we want to do yet. If we run main up here, we'll see, no, that's not main. Primer has evaluated this program by calling map on the input list and generating an output list. Note that there's a hole in the output, so we can actually run incomplete programs. You can do this up to a point in GHC. You can use type holes and defer type errors, but if you then try to print a list which contains things that are not yet defined in it, it won't print you the list with the holes in it. It will just panic, which is fair enough. But we can allow students to define incomplete programs, and then if they want to then go back later and complete them, then they can. So that we always make sure that programs are valid at all times, and that includes that we can, for example, modify type defs. If we say we want to change our Boolean type to have an undefined case, which is obviously a terrible idea, then all parts of the program will adjust to that change, and branches will contain the undefined. Or if we wanted to change our T to have some extra fields, those get generated down here, and even the evaluation updates accordingly. I think those are all of the main features I was supposed to show off, and if they're not, then I'm basically running out of time. So, very recently, and this weekend functions as an announcement of sorts, we have open sourced both our backend, which is the language implementation, including the evaluator, type checker, etc., for what is essentially a sort of minimal functional language, and that could probably be adapted to other uses. And that's a Haskell library, of course, otherwise I wouldn't be on this stage. And then we have the front end, which unfortunately is not built in Haskell. That's a React TypeScript front end that is fairly simple. Very much the bulk of the code base is this Haskell library, and then the front end just sort of knows how to draw trees and how to render actions. And yeah, those are both available on GitHub, and there's a Primer channel on Discord if you've got any further questions for us, and we'll hopefully be hanging out in a sort of workshop room tomorrow, if not this evening. There's all sorts of things we want to do in future that I'm probably not going to get to dwell on now, but interactive program execution, rather than the one-shot mode we currently have, we want to be able to sort of step through one evaluation step at a time, one beta reduction, etc., and allow students to really walk through the evaluation of their programs. We want to have better error messages. By error messages, we mostly mean that this type doesn't match the whole kind of things, because we don't have the same kind of errors as such. Although there are other cases like variable capture, where we want to clearly explain to the student what has gone wrong in their program and what they can do to fix it. And then the big one is side effects. At some point, this needs to go beyond just being able to do sort of discrete maths, and actually students are going to want to build interesting programs. And we got all sorts of ideas for plugins there. For generating music or animations or whatever, but that's going to come. And we don't know whether we'll end up using some sort of Haskell-style monadic I/O and quite how that would fit or whatever, but it's an interesting challenge. Right, that's everything. So come and chat to us afterwards if you've got any, or if you've got any questions now, if we've got time. No. Okay, come and chat to us afterwards if you have. I'll be here. Thanks.